Chapter we'll talk about comparing two proportions. Some of the concepts: two sample problems involving proportions, the sampling distribution of a difference between proportions, large sample confidence intervals for comparing proportions, accurate confidence intervals for comparing proportions, and significant tests for comparing proportions. So, suppose we want to compare the proportion of male students who have jobs to the proportion of female students who have jobs. The ideal strategy is to take a separate random sample from the population of males and the population of females and compare the sample proportions. What if we want to compare the proportion of side effects of drug A and drug B in a randomized experiment? This time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. We use the proportions of successes in the two treatment groups to make the comparison. So, the table that summarizes these two situations. We have two populations, or two treatments. Each has an unknown parameter, P1 and P2. And we take samples from each population and calculate the sample statistics, that is the proportion in one sample, the proportion in the other, and we need to know the sample sizes of each sample. Now, to talk about the sampling distribution of a difference between proportions. So if we choose a simple random sample size of N1 from population 1 with proportion of successes P1, and an independent simple random sample of size N2 from the second population with a proportion of successes P2. The shape of this distribution. When the samples are large, the sampling distribution of P hat minus P hat for two different samples is approximately normal. Again, the difference between P1 and P2 is fixed. Those population proportions have some value. So we're considering taking different samples and looking at the difference of the sample proportions and plotting those. So again, the differences between sample proportions is approximately normal. The mean of the sample distribution is the difference between the population means. So we can use the sample proportions to estimate the difference in population proportions. And the standard deviation of the sampling distribution of sample proportions is given by this formula, similar to the standard deviation we had for two sample means. So we have this layout. The sampling distribution of the difference between sampling sample proportions. The values fall along the horizontal axis. The mean of this distribution is actually the difference between the actual population means, and the standard deviation is given by that formula. So when the data come from two random samples or two groups in a randomized experiment, the statistics P hat 1 minus P hat 2 is our best guess for the value of P1 minus P2. We can use our familiar formula to calculate a confidence interval for the difference between population proportions. That is the statistic, the sample value, plus or minus the critical value times the standard deviation of the statistic. When the independent condition is met, the standard deviation of the statistic for P hat 1 minus P hat 2 is sigma equals this value. Once again, we don't know what the population values are, so we replace them in the standard deviation formula with sample proportions. And the result is the standard error of the statistic P hat 1 minus P hat 2. So here again, we've just replaced the population proportions with sample proportions. And that's the standard error. So when the random and normal conditions are met, an approximate level C confidence interval is given by the difference in the sample proportions plus or minus a margin of error. which is the critical z-value associated with the confidence level, times the standard error. The data are produced by a random sample of size n from population 1 and a random sample of size n2 from population 2. The counts of successes and failures in each sample must be at least 10, all of them. So we have 4 values to check. So here's an example. As a part of the Pew Internet and American Life project, researchers conducted 2 surveys in late 2009. The first survey asked a random sample of 800 U.S. teens about their use of social media and the Internet. A second survey posed similar questions to a random sample of 2,253 U.S. adults. In these 2 studies, 73% of teens and 47% of adults said that they use social networking sites. Use these results to construct and interpret a 95% confidence interval for the difference between the proportion of all U.S. teens and adults who use social networking sites. So the parameters of interest, P1 is the proportion of all U.S. teens who use social networking sites. P2 is the proportion of all U.S. adults who use social networking sites. And we want to estimate the difference between these two with a 95% confidence level. So we're going to use a large sample confidence interval for P1 minus P2 if the conditions are satisfied. Is it random? Well, we're told that it's random. We count the counts of successes and failures and note that the normal condition is met since they are all greater than 10. If conditions are satisfied, we can construct a 2-sample z-interval for the difference in population proportions. So the formula, we plug in all the values. The first sample proportion is 0.73, the second is 0.47. So we look at the difference, plus or minus the critical z-value, 1.96, times 0.73 times 0.27 over 800, etc. You can do the math. So we have 0.26 plus or minus a margin of error of 0.037. The confidence interval is 0.223 to 0.297. So we conclude that we're 95% confidence that the interval from 0.223 to 0.297 captures the true difference in the proportion of all U.S. teens and adults who use social networking sites. So this actually suggests that there are between 22 and 29% more teens than adults in the U.S. who engage in social networking. Large sample confidence interval for a single proportion. The large sample interval for comparing proportions generally has a true confidence level less than the level you asked for. So once again, we'll add imaginary observations to improve the accuracy. So we choose independent simple random samples from 2 large populations with proportions P1 and P2. To get the +4 confidence interval for the difference between proportions, we add 4 imaginary observations. 1 success and 1 failure in each of the 2 samples, and then we add 2 to each sample size. And we can use this interval when the sample size is at least 5 in each group, with any counts of successes and failures. Example of the +4 confidence interval. How much does the cholesterol-lowering drug gemfibrozil help reduce the risk of heart attack? We compare the incidence of heart attack over a 5-year period for 2 random samples of middle-aged men taking either the drug or a placebo. And out of 2,051 taking the drug, 56 had heart attacks. Out of 2,030 not taking the drug, 84 had heart attacks. So we first need to calculate the +4 proportions for each sample. So P1 twiddle is the number of successes plus 1 over the sample size plus 2. That's 56 plus 1 over 2051 plus 2, which is approximately 0.0278. And the same for the second proportion sample. 84 plus 1, etc. So we get 0.0418 for the proportion for the second sample. We use these numbers in the confidence interval formula. So here we just plug in the numbers and do some calculations. We get the difference between the sample mean proportions is minus 0.014. The margin of error is plus or minus 0.0094. Or the confidence interval is from minus 0.0234 to minus 0.0046. We conclude that we're 90% confident that the percentage of middle-aged men who suffer a heart attack is 2.34% to 0.46% lower when taking the cholesterol-lowering drug. Significant test for comparing proportions. An observed difference between two sampled proportions can reflect an actual difference in the parameters, or it may be just due to chance variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. So to do a test, we standardize the difference between sample proportions to get a z statistic. Z equals the difference in the sample proportions minus 0. Keep in mind, 0, we're assuming that the difference between the population proportions is 0, and we divide by the standard deviation of the statistic. So if the null hypothesis that the population proportions are equal is true, the two proportions are the same. We call their common value p. But now we need a way to estimate p, so it makes sense to combine the data from the two samples. This is called the pooled or combined sample proportion, and this is simply the count of successes in both samples combined divided by the count of the individuals in both samples combined. So, to do a significance test for comparing two proportions, we draw a simple random sample of size n1 from a large population having a proportion p1 of successes, and we draw an independent simple random sample of size n2 from a large population having proportion p2 of successes. To test the hypothesis that the two population proportions are equal, that their difference is 0, first find the pooled proportion, p hat, of successes in both samples combined. Then compute the z statistic, as shown here, using that value, the pooled value. And the typical alternative hypotheses, if the difference is positive, if the difference is negative, or if the difference is simply not 0. Example. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in two low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, a simple random sample of 150 students included 26 who had not had breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions? And we'll carry out a significance test at the 0.05 level. So our hypotheses, the null hypothesis, the difference between the two populations is 0. There's no difference between them. And the alternative hypothesis is that the difference is not 0. And P1 represents the proportion at School 1, and P2 represents the proportion of all students at School 2 who didn't eat breakfast. So we check the conditions. The data were produced using two simple random samples, so that condition is met. We check the counts of successes and failures, and note that this condition is met since they are all greater than 5. I should point out here, for example, in School 1, there are 80 students who, 19 students who didn't eat breakfast, so that's the number of successes, and then 80 minus 19 is the number of failures. And School 2, 26 is the number of successes, and 150 minus that. So clearly those are both bigger than 5. The condition that the number of successes and failures have a certain number ensures that the distribution is normal. And that's really important because we're using z-scores. So that's the main reason that we need to count this, check this out, is to make sure that the underlying distribution is normal. Okay, so the conditions are met. We'll use a two-sample z-test. So we take the pooled numbers here, the number of successes in both samples, and we add them, 19 plus 26, and the number of observations in each sample, and we add those, 80 plus 150. We get 45 over 230. So our pooled estimate for the population proportion is 0.1957. And then, to calculate the z-score, we plug those numbers into the formula. So notice the pooled value is in the denominator, whereas the difference in the sample proportions is in the numerator. So we crank out the numbers, we get a z-score of 1.17. This is a two-tailed distribution test, so we want twice the value of a z-score of greater than 1.17. So using table A, we find that the z-value here, the p-value here is 0.2420. So since the p-value 0.2420 is greater than the chosen level of significance, we fail to reject the null hypothesis. There is not significant evidence to conclude that the proportions of students at the two schools who didn't eat breakfast are different. Here's another example. Gastric freezing was once a treatment for ulcers. Patients would swallow a deflated balloon with tubes, and a cold liquid would be pumped for an hour to cool the stomach and reduce acid production, thus relieving ulcer pain. The treatment was shown to be safe. It significantly reduced ulcer pain, and so it was widely used for years. A randomized comparative experiment later compared the outcome of gastric freezing with that of a placebo. 28 of the 82 patients subjected to gastric freezing improved, while 30 of the 78 in the control group improved. The sample proportions for the first sample for the gastric bypass, 0.341, improved. For the second sample in the placebo group, 0.385 was the proportion that improved. So the hypotheses, the null hypothesis is that the proportions for each population is the same, so the difference is 0. The alternative hypothesis is that the proportion for the population of gastric freezing is greater than the proportion in the placebo group, so their difference is positive. The pooled proportion we'll use for the populations combined is the sum of the population successes, the proportion of the sample successes divided by the sum of the sample sizes. So in this case, that's 0.3625. And then we have the formula for the z statistic, the difference in the sample proportions divided by the standard error in which we're using the pooled proportion for the population. So the z-score here is minus 0.499. Now, once again, the p-value is the probability of obtaining a z-score greater than minus 0.499. From table A, we get a p-value of 0.69. It's shown in the shaded region on the normal curve. So the gastric freezing was no better than a placebo, and the treatment was abandoned. In the first case, they did not compare this to any control. So there was no reason to think that it was better, worse, or anything. They just assumed it was better. In this case, the randomized comparative experiment showed that it really doesn't matter. So always use a control. So to review, we described the sampling distribution of a difference between proportions, described and checked the conditions necessary for inference, construct and interpret large sample and accurate confidence interval for the difference between proportions, and conducted a significance test for comparing two proportions. Actually, two.